Welcome to this comprehensive tutorial. Today, we're embarking on an exciting journey into a fundamental and incredibly powerful tool for managing game flow and object behavior within Unity, the state pattern. This session is meticulously designed for beginners in game development, ensuring we'll proceed step by step, breaking down complex concepts into easily digestible parts. Our goal is to empower you to write cleaner, more organized, and ultimately more manageable code for your Unity games, laying a solid foundation for future projects. So, let's begin by demystifying the state pattern. At its core, it's a behavioral design pattern that enables an object to dynamically alter its behavior when its internal state undergoes a change. To grasp this concept intuitively, consider a simple analogy, a common light switch. The light switch itself doesn't change, but its functionality, whether it turns a light on or off, is entirely dependent on its current state, be it on or off. This pattern allows for a clear separation of concerns, making your code more modular and easier to understand. In the dynamic world of game development, this pattern proves to be exceptionally well suited for orchestrating distinct game phases. Imagine managing your game's main menu, the intense active gameplay, or the conclusive game over screen. Instead of wrestling with a convoluted and often error-prone web of if-else statements that can quickly become unmanageable, the state pattern offers an elegant solution. It allows us to encapsulate the unique logic and behavior for each of these distinct states into its own dedicated class, leading to significantly cleaner and more maintainable code. The state pattern is structured around three pivotal components, each playing a crucial role in its implementation. First, we have the context. This is the central class whose behavior will dynamically change based on its current state. In the context of our Unity game, this will typically be a game manager, responsible for overseeing the overall game flow. Second, there's the state interface. This interface acts as a contract, defining a common set of methods that all concrete states must implement, ensuring consistency across your state-based behaviors. And third, we have the concrete states. These are the individual classes that implement the state interface, each representing a specific state, such as a menu state, a play state, or a game over state, each with its unique logic and actions. Let's dive into the practical implementation. Our very first step is to formally define our state interface. Open up your Unity project and create a new C# script. We'll name this script iState. Within this interface, we will declare three essential methods that every single one of our game states must rigorously implement: enter, update, and exit. These methods will serve as the foundational structure for how each state behaves and transitions. Let's elaborate on the purpose of each method within our iState interface. The enter method is designed to contain all the logic that needs to execute precisely once when we initially transition into a particular state. This could involve setting up UI elements or initializing variables. The update method, much like Unity's own update function, will run continuously on every single frame while the object is in that specific state, handling ongoing logic and input. Finally, the exit method is crucial for managing any necessary cleanup or deinitialization tasks when we transition out of a state, ensuring a smooth and clean handoff to the next state. Now that our interface is defined, let's proceed to implement our very first concrete state, the menu state. Create another new C# script and name it menu state. This class will rigorously implement our iState interface, adhering to the contract we just established. Furthermore, it will require a reference to our future game manager. This reference is essential because it will enable the menu state to effectively trigger and manage state changes, allowing the game to transition from the menu to other states like gameplay. Within the menu state class, the enter method is where you would typically activate and display your main menu user interface elements. For the purpose of this tutorial, we'll simply add a debug log message to confirm entry into this state. The update method will be responsible for continuously monitoring for player input, such as pressing the spacebar, which will then initiate a transition to the play state. Finally, the exit method will log that we are leaving the menu state and would be the appropriate place to disable or hide the menu UI, preparing for the next game phase. Moving forward, our next concrete state is the play state. This state will follow the exact same structural principles as our menu state. Begin by creating a new C# script file and name it playstate.cs. Within this file, ensure that your playstate class correctly implements the iState interface. The enter method for the playstate is where you'll initiate core game logic, such as spawning the player, setting up the game world, and enabling player controls. For now, we'll simply log entering playstate to visually confirm its activation in the console. In the playstate's update method, this is where the heart of your core game loop will reside. This method will continuously execute, handling all ongoing gameplay mechanics, player actions, and enemy AI. Crucially, this is also the designated place to check for specific conditions that necessitate a state change. For instance, you might check if the player's health has reached 0, which would trigger a transition to a game over state, or if the player presses the escape key, prompting a return to the menu state. The exit method, conversely, will be responsible for gracefully stopping all active game logic and disabling player controls, preparing for the next state. Our final essential state for this tutorial is the game over state. To implement this, create a new C# script file and name it gameoverstate.cs. The enter method within this class will be responsible for displaying the game over screen to the player, potentially showcasing their final score or other relevant statistics. The update method will then listen for player input, such as pressing the spacebar, to allow them to restart the game, which will transition us back to the menu state. Finally, the exit method will handle the task of hiding or deactivating the game over screen, clearing the way for the next game cycle. With all our individual states now clearly defined, the next critical step is to create the context that will manage these states. This context will be our game manager. Since it needs to exist within our Unity scene and interact with game objects, it will be a mono-behavior. Therefore, create a new C# script named gameManager.cs and then attach this script to an empty game object within your Unity scene hierarchy. This game object will serve as the central orchestrator for our game's state transitions. Inside the GameManager script, we will declare a private variable of type iState, which we'll name _currentState. This variable will hold a reference to the state that is currently active in our game. The most pivotal component of our game manager will be a public method named setState. This method is specifically designed to handle the transition logic between different states in a safe, controlled, and predictable manner, ensuring that state changes occur smoothly and correctly. When the setState method is invoked, its first action is to meticulously check if there is an existing active state. If a current state is indeed present, it then proceeds to call that state's exit method. This step is absolutely crucial for performing any necessary cleanup or deinitialization tasks associated with the outgoing state. Following this, the method assigns the newly provided state to our _currentState variable. Immediately after this assignment, it calls the new state's enter method. This precise sequence ensures a clean, efficient, and well-managed handoff between states, preventing any lingering effects from the previous state and properly initializing the new one. To initiate our state machine and get things running, within the Game Manager's start method, we will set the initial state of our game to a new instance of the menu state. This ensures that our game begins at the main menu. Subsequently, in the Game Manager's update method, we simply perform a quick check. If the _currentState variable is not null, meaning there's an active state, we then call its update method. This elegant delegation ensures that the frame-by-frame logic and behavior are handled by whichever state is currently active, maintaining a clean separation of concerns. Let's observe our implementation in action within the Unity editor. Navigate back to Unity and press the play button. You should immediately see entering menu state displayed in your console window, confirming our initial state. Now, press the spacebar on your keyboard. The console will then show exiting menu state, followed almost instantaneously by entering play state. This sequence of messages unequivocally confirms that our state transition mechanism is functioning precisely as intended, moving seamlessly from the menu to the gameplay state. Continuing our demonstration, if you are currently in the play state and press the escape key, you will observe a smooth transition back to the menu state, as defined in our playstate's update method. Similarly, if a specific game over condition were to be met during gameplay, the system would automatically transition to the game over state. This clearly illustrates how each distinct piece of game logic and behavior is neatly and independently contained within its own dedicated state class, promoting modularity and clarity. So, one might ask, why invest this effort into implementing the state pattern? The benefits are truly immense and far-reaching. Firstly, your codebase becomes incredibly organized and structured. Each state's specific logic is encapsulated within its own dedicated file, making your code highly modular, exceptionally readable, and much easier to navigate. This represents a monumental improvement over attempting to manage complex game flow within a single, monolithic script riddled with intricate and often confusing conditional logic, which can quickly become a maintenance nightmare. This superior organization directly translates into significantly increased flexibility and maintainability for your game project. Need to modify how your main menu functions? You simply open menustate.cs, make your changes, and you can be confident that these modifications won't inadvertently disrupt or break your core gameplay logic. Furthermore, adding an entirely new state, such as a paused state, becomes a remarkably straightforward process, as simple as creating a new class that correctly implements the iState interface, seamlessly integrating it into your existing state machine without extensive refactoring. For those of you just starting out, my strongest advice is to begin with a simple, clear implementation, much like the one we've explored today. Always strive to use clear and descriptive naming conventions for your states, methods, and variables. This greatly enhances code readability and understanding. As you gain more confidence and experience, you can then begin to integrate this powerful pattern with other advanced Unity features, such as the animation system, to create visually appealing and dynamic state transitions, or the input system for more sophisticated control schemes. By diligently implementing the state pattern, you are actively building a robust foundation for creating scalable, highly flexible, and easily maintainable game code. This isn't just a design pattern. It's a fundamental architectural concept that will undoubtedly serve you exceptionally well as you progress to tackle more complex and ambitious game development projects. Thank you for joining me in this tutorial, and I wish you happy and productive coding.